So welcome back. The topic this week is a continuation of where we ended last week, and what we are going to do today is to try to wrap up the discussion on ridge and lasso and link that with a discussion of the statistical interpretations of these methods. And hopefully that may give us a deeper intuition about what these methods are about. When we're done with that, we are going to use these kind of statistical interpretations to move over to resampling methods. And these are methods which are very important in a statistical data analysis, because often we are limited to very few data. Many of the machine learning methods are, however, data hungry, which means that you need to have lots of data. And one of the ways to compensate for that, which in addition gives you better estimates of specific expectation values like the mean value, the variance of specific quantities, but also better estimation of the mean squared error in case of regression, is the technique of resampling methods. And resampling methods allow us, by reshuffling the data, in a certain sense to create a new data set. And these are important techniques, and some of the most used methods in this kind of resampling of the data are cross-validation and also the bootstrap method. Okay, so let's get started with the topic today. And this, as I said, this is a continuation of what we did last week, which was session number 4. And so we're going to wrap up our discussion about ridge and lasso regressions, and then we're going to look at statistics, probability theory, and resampling methods. So one of the things which we did last week was to discuss the mathematics of ridge and lasso regression. So the standard ordinary least squares contains just a standard mean squared error, which we now have rewritten in terms of this norm 2 of a vector. And the way we added the ridge regression was simply to add a parameter lambda here, multiplied with the parameters beta. And as we saw last week, what this did was in a way to dampen away those contributions which were less important. On the other hand, when we looked at the lasso optimization, what happened then is that we actually ended up by reducing or even taking away some of the features which were less important. We actually sent the parameters beta, in this particular case, to 0. And here we have defined the norm 1 of a given vector, which is just the sum of the absolute values. Then what we did was to look at the different codes where we played around with ridge and lasso regression, and we saw this explicit reduction of those parameters which could be less important. So it's a way to actually reduce the dimensionality. Now what it means is that when we are fitting a problem, ridge and lasso regression could actually give us a mean squared error which could be better. In many cases, when we deal with ordinary least squares and fitting a polynomial, it often happens that the ordinary least squares is the method which does the best job. However, when we have data with lots of correlations and where the different features may not be fully independent, what we may often experience then is that by adding this tuning parameter lambda, which we have here, we may actually get a better variance for the unknown parameter, which means that they are have a less deviation from the mean value, and at the same time we may even get a mean squared error which is smaller. But this is something which we cannot tell in most cases a priori whether it will give us a better result or not. So I'm going to skip some of the codes which we discussed last week, and we are going to dive now into the statistical interpretation of lasso and ridge regression. So these are the examples which we discussed last week. I'm not going to repeat them. You could take a look at the codes. But what I wanted to go back to now is actually where we left last week, and that is to link the regression analysis with a statistical interpretation, because that hopefully may give us a slightly deeper intuition about region lasso regression. And I will try to demonstrate why. And then after the break, we are going to start looking at resampling techniques. So one of the things which we also discussed last week was about the covariance. Now we have assumed that our data follow are given by a given function f, which is a deterministic function, which means that there is no stochasticity in that specific function. But it has our data sets, the output, have a noise which we assume is to be normally distributed with a mean value 0 and a standard deviation which is given by sigma, which means that we have a variance sigma squared. And these quantities are assumed to be independent and identically distributed, which means then that the covariance is equal to 0 unless we have the same variable epsilon I1 and epsilon I2 here. And the randomness of these epsilons implies that y of I is also a random variable. And as we saw last time, this y of I is normally distributed because it has a mean value which is given by this x multiplied with a parameter beta. And this is a non-random scalar. And the expectation value of a scalar is a scalar. Now, one of the things which we then went through last time was actually to look at the expectation values of these given quantities. So let me quickly remind you of that. And also, as an exercise, which we gave you last week, was to go through these slides and make sure that you actually agree with some of the derivations here. So the nice thing with the linear regression is actually that we end up with analytical results for the important expectation values. Keep also in mind that in standard machine learning, we do not have the probability distribution behind the given events. So often in standard machine learning, we are not that much interested in that. We are more interested in making a model with which we can make predictions on data which has not been included in the training. And then we are also interested in correlations. And correlations is something which we can extract from the covariance. Or if we take the covariance and divide by the variance, we get something which is called a correlation matrix. And these are quantities which are often used to analyze our data and to find whether there are specific features which are strongly correlated or not. So just to give you an example, if you're looking at, let's say, housing data, we assume and we expect actually that the price of the house is correlated with the number of rooms the house has, the size of the house. The more rooms, we expect that the price would be higher. And this will be reflected in the data set in the sense that if we were to calculate the covariance between these different features, like the price, the average price of a house, and the number of rooms, we would find a strong correlation between the number of rooms and the price of the house. So these are typical things which we can infer from the data when we have made such a fit to a model, or even if we just take the specific features and look at our design matrix, as we discussed last week, and we calculate the correlation or the covariance matrix based on the design matrix. Now, what we did last week was then to run through some of these calculations. And since EPS, the expectation value, so this stands for the expectation value, we are looking at the sample means, which means that we don't have a probability distribution, but every data entry has the same likelihood. So we divide by a factor 1 over n, which is the number of entries. And then since xi, which is the design matrix, the specific row, multiplied with the column vectors here, then we have as a result just a scalar, which is this quantity you see here, just a number. And then we have the expectation value of the epsilon i's, its mean value, which is just set to 0. We can then calculate also the variance of the quantities y of I, and we can show that this is actually given by the variance of the normally distributed noise. So from that we can infer that the output follows a normal distribution with a specific mean value and a variance which is given by the same variance as the normal distributed noise. So when we do this, we can also calculate the expectation value of the parameters beta. So if we take ordinary least squares, we can then find that this beta is just equal to its own value. So we normally say that the parameter is unbiased. So recall again that we made an assumption when we derived ordinary least squares that these parameters beta are deterministic quantities or non-stochastic quantities. We are not limited to do that, and we are coming back to possible ways to define a distribution for the parameters beta. And we will use that in particular when we are going to study ridge and lasso regression from a statistical point of view. So for this lecture I will use slides for quite a lot. I hope that's okay. I mean, I like to use the whiteboard as well in order to break the monotony, but there is some material here which I wanted to cover by going through the slides here. Now you can calculate the variance of beta here, and you can actually find that the variance of beta has also an analytical expression given in terms of the inverse of the design matrix transpose times the design matrix. And that's also an extremely useful quantity. And if you do the same with ridge, you would find that with ridge you simply have to add this parameter lambda, and you can also calculate the variance for ridge regression. So I'm just stating the expressions here, and then you can calculate the difference between the variance for ordinary least squares and ridge, and you can find that the difference is non-negative since each component of the matrix product is non-negative definite. And that means that the variance we obtain with the standard ordinary least squares will always, for a given lambda larger than 0, be larger than the variance of beta obtained with the ridge estimator. And this is going to have very interesting consequences when we look at the quality of a given model in terms of the standard deviation on the parameters beta. And that leads also to when the variance is smaller with ridge regression, it means also that the confidence intervals for our mean value beta are going to be smaller than those with ordinary least squares. And these are also important statistical properties, which means that we can tune a model which has in general a smaller mean squared error. We are coming back to these things. So where I wanted to start now is by bringing back what we discussed last week and show you how you can derive ordinary least squares using a statistical interpretation, and that means that we start from a probability distribution. Now the way we set this up then is that we have now inferred from the mean value of the output variables y of I with a given input and the parameters beta, the optimal parameters, then we can find a probability which determines a given output y of I in terms of a normal distribution. And this is something which we would postulate by the standard Gaussian distribution, because now the mean value is different from 0. So the sigma squared here is a quantity which we in general do not know. Sometimes you may have data sets which come with a given standard deviation, so we could use that one. But in most cases we do not have the value sigma, and then people just tend to put sigma equal to 1. And you will often see that in modeling this normally distributed noise, this is actually the approach which many people take, many practitioners take, when they don't have any idea what the value sigma squared should be. So this means that what we did last week was now to define a probability, and we assume, these are important assumptions, we assume that the y of i's are independent of each other, which means that we can actually write a total probability as a product of all the individual probabilities. And we have also assumed that these parameters beta are the parameters we want to estimate. By that, we can construct what we normally call the total probability distribution for all the events y and x with a given beta. So this bar here is normally written, this vertical line here is normally written as the given a parameter beta. So what is the likelihood for y with a given x and given beta? So this is now the product of all the individual probabilities. And the domain of events is now given by the x's and the y's. And we would typically rewrite this in terms of a d, which is a domain, and then a given parameter beta. So this is the likelihood of a specific output d with a given parameter beta. Now, what we did last week was then to find the parameter beta by assuming that we want to have the maximum likelihood. So keep in mind that when we are now deriving the equation for the parameters beta, we are simply assuming that we want the maximum likelihood. Nobody's looking after the minimum likelihood for an event. So we want to find the parameters beta which maximize the likelihood for a given output. So that leads to a naming in the statistics literature, which is called maximum likelihood estimators. So betas, which we have been calling for our parameters, they also call the estimators, or the estimators of the model which we have chosen. And in our case, it's a linear model. So in this particular case, what we are looking at now is the maximum likelihood with a given beta. And that leads to the maximum likelihood estimators. So in statistics, maximum likelihood estimation, there's a method of estimating the parameters of an assumed probability distribution, given some observed data. And that's achieved by maximizing a likelihood function, so that under the assumed statistical model, the observed data is the most probable one. And then we assume here that our events are given by the above Gaussian distribution, and then we'll simply determine the optimal parameters. Now, in practice, if you look at derivatives of products, this is something which normally is more cumbersome from a computational point of view and can easily lead to overflow or underflow problems, with loss of numerical precision as one possible consequence. So what is more convenient, and this is a totally equivalent problem, is actually to maximize or minimize the log of the probability distribution. That means if we go back to this equation here, if we now take the logarithm of this function, and this is a monotonously increasing function, so we can maximize that, or we can take the negative log and then we can minimize it, because then it's a continuously decreasing, monotonically decreasing function. So these are the kind of strategies which we end up, and if we take the log of this function here, that's a quantity which is much easier to deal with, because it's simply going to be a sum of products. And a sum of the log of the products. If we, on the other hand, want to compute the products, we know that each term can become pretty large, or can be very, very small. And when we multiply a very, very large term with a very large term, this can lead to quantities which go beyond the number of real numbers which we can represent in a computer. Or if we have very, very small numbers, we may get something which is called underflow, which means that we actually have numbers which are so small that they cannot be represented properly. And that can lead to potential problems of loss of numerical precision. So from a computational point of view, what we often do then, and I see there should be a parenthesis here, so I've missed one parenthesis, we take the negative log, and that leads to simply a sum here. And that's an equivalent problem, which means then that when we look at the quantities here, this simply becomes a constant which we have here with the number of events which we have. and then plus something which looks pretty much like the standard mean squared error. And this is a quantity which we can take the derivative of. And if we take the derivative of this quantity, we know that the first quantity is a constant. And then we take the derivative with respect to beta, and that leads to the same equations which we had with ordinary least squares. So we can actually derive the same type of equations using two different strategies. One, which is the one we started with, which is a plain linear algebra perspective, or we can now assume that there is a distribution which governs the events gamma, the outputs y, not gamma but y, sorry. And with that, we get back the standard equations for the optimal parameters, or the estimators, as we've also been calling them, for ordinary least squares, OLS here, which are given by the equation we got from linear algebra. Now, we are going to use this as an input to the discussion of ridge and lasso regression in terms of statistics. However, before we do that, we need to look at something which is called Bayes' theorem. And Bayes' theorem plays a central role in statistics, and in statistics it can be compared with Pythagoras in geometry. So let's take a look at some basic statistical properties. But before we move on, let me know if there are some questions. So this was roughly a review where we ended last week, and this is a topic which now becomes relevant for both the statistical interpretation but also for the basis for resampling techniques. So any questions so far before we move on? Okay, so the what we can do now is actually to take a look at some basic statistics, and one of the central theorem in statistics is actually Bayes' theorem, and it plays a similar role, as I said, to Pythagoras in geometry. So before we do that, we need to remind ourselves of some basic statistics. So we know that the union of events is normally given by the probability of P of x plus P of y if we have two events, x and y, minus the disunion of them. And we also have the product rule, which we can rewrite like this Px of y here, which is now given by the probability of x given y multiplied with the probability of y, or alternatively as the probability of y with a given x multiplied with the probability of having x. This is the way you would read the standard product rule. And if these events are independent, then it's simply the probability with respect to x multiplied with the probability with respect to y. You could think of this in terms of quantum mechanics. And if you think of quantum mechanics, if you have two non-interacting particles moving in a harmonic oscillator trap, then the total wave function is just the product of the two single particle wave functions, which means that the probability of finding these two particles in a given state is given by the wave functions of the individual particles squared, multiplied with each other. So that's a typical example of another probability of independent and identically distributed events. So if we have independent events, then clearly we can rewrite this equation here for the product rule in terms of just the probability of P of x and P of y. So I hope these are things which many of you have seen before. So if we move on a little bit, what we can also define now is the marginal probability. And that is defined in terms of only one of the set of variables. So for a discrete probability, for instance, which is often the case which we end up with looking at, if we sum over all the y's, we would then sum over these events, which means that we would have the probability of x with a given y multiplied with the probability of finding this value of y, which we would write in a more compact way as the equation which you see here. So in a sense, this is just a way to either sum away one of the variables, or if you have a continuous distribution, it will be the same as integrating over the variable y. So we end up with something which is a probability which depends only on one of the variables, and that's called the marginal probability. And I guess you've seen equations like this many, many times. Then we can define the conditional probability. And that's simply us going back to the equations which we had before. So we have px of y here. We just divide with p of y, assuming that p of y is larger than 0, obviously. And p of y can be determined in terms of the marginal probabilities. And then we have px and y here. That's normally called the conditional probability. Then, what we can do then is to, from the conditional probability, we can obtain Bayes' theorem. And Bayes' theorem simply uses the expression for the conditional probability. It takes the marginal probability for p of y here, and then it simply rewrites this in terms of the product of the probability of having y with a given x and p of x, and then divided by a factor here which serves to normalize the probability. So you can easily now here interchange x with y. So the way you read this is the probability of x with a given y, and assuming now that we know the probability of y with given x multiplied with p of x, we're assuming that we actually know these quantities or can model them in some way, then we can always set up the probability of x given y. Now this is going to be interesting for us when we want now to link this with ridge and lasso regression. So this is Bayes' theorem, and it plays a central role in machine learning as well, especially if you want to bring in probabilities. There's the exciting field of what's normally called Bayesian machine learning, which we will unfortunately not have enough time to touch upon. But anyway, these quantities, if we take out the normalization factor which you have in the denominator, these quantities, this p of x is normally called a prior, and this py of x is called a likelihood. This probability here on the left hand side is called a posterior probability. So prior would be you having a model for the x's. It could be a uniform distribution. If you don't know anything about the probabilities of the x's, then you could assume that every x has the same likelihood. And the py of x is then a probability which you also have a model for. And based on these, we can try to find a final probability and then compare this probability with experimental data, for instance. So let's now move on to a specific example. I just want to say that the quantity py of x on the right hand side of the theorem is evaluated for the observed data y and can be viewed as a function of the parameter space represented by x. It's not necessarily normalized and is normally called the likelihood function. The function p of x is called the prior, while the function on the left hand side is normally called the posterior probability, the final probability. So just to give you a small example, if this p of x is a uniform distribution, that means it just gives a constant for all the events x's. If py of x is a normal distribution, that means that the new distribution would also be a normal distribution multiplied with a multiplicative factor from the prior distribution p of x. Now let's look at an example in order to get some kind of feeling of what Bayes' theorem implies and why it is important to think of Bayes' theorem or think in terms of Bayes' theorem. So an interesting case now where the probability can be deceiving and may lead you to think that you do have cancer is actually to look at results from a mammography. And this mammography scans they are used to actually rule out breast cancer cases, and it's normally offered to every woman between 45 and 70 in most countries, at least in Europe and in Northern America. So, and this is used actually to prevent or discover at an early stage breast cancer, which is a very common, unfortunately, a very common type of cancer. So we have now to be a little bit careful in the way we word things. And this is where Bayes' theorem here actually gives us the right interpretation. So you could define the sensitivity for a positive event by a variable x. And then it takes binary values with x equal to 1, which represents a positive event. And you could say that a positive event would be not having cancer, or you could take the opposite. And x equals 0 being a negative event. And then we reserve y as a classification parameter for either negative or positive breast cancer confirmation. So positive here is going to be actually a negative message, which means that we have breast cancer, and negative would mean the same as not having. So what we are going to let y be now, so x is a positive or negative outcome from a mammography scan. That does not mean that you do have cancer. That's the important thing to keep in mind here. So the y variable is actually the one which is interesting for us, because that's the one which tells us the probability of having breast cancer or not. So if you assume that you do have breast cancer, then the test will be positive with a probability of 80%. So these are just numbers which I've cooked up here. This sounds scary because you think, wow, there's an 80, if the test is positive, there is an 80% probability that they have breast cancer. However, this conclusion is not correct. And the way you should actually read this is in terms of a Bayesian analysis. And that's going to give you the correct probability. If you now have a positive event from the mammography, that means x is equal to 1, then you want to find out what is the probability of having breast cancer. So this is only the positive probability of having, this is the probability of a positive event from the scan in case you have cancer. That does not mean that you have cancer. So if you now look at the what we would call the prior, in a population as a whole, there is roughly 3 to 4 per mil of women which get breast cancer in the age of 45 to 70. And this is the kind of quantity which would define the prior. I'm also making up a number here which calls a false positive result, which means false alarm. And that says that x equal to 1 with y equal to 0 is equal to 0.1. Now what we can do then is to actually use Bayes' theorem to find the posterior probability that the person has breast cancer in case of a positive test. So this is the way we should ask the question: what is the probability of having breast cancer, y equal to 1, in case of a positive test, x equal to 1? So that's given by x equal to 1, the measurement, with you inputting y equal to 1, multiplied with the prior probability of having breast cancer. And then you divide by the normalization factor. And that means that if you now test positively, then the probability of having breast cancer is 3%, which sounds much, much better than 80%, which we looked at in the previous slide here. So this is a matter of wording. What kind of probabilities are those which we are looking at? So Bayes' theorem gives us then a tool to perform this analysis. Now what we're going to do next now is actually to go back to our discussion of lasso and ridge regression. And now I'm just going to try to break the monotony a little bit with going back to the whiteboard. So let's do that, and then set up the expressions for ridge and lasso regression, derive them based on a statistical interpretation. And that gives us hopefully a slightly deeper insight about what's going on. So I'm going to just switch to the whiteboard here. So if we now look at the statistical interpretation of ridge and lasso, let's now remind ourselves of standard ordinary least squares. So in the ordinary least square case, what we assume now is that this probability of the given result D, this is a domain, so it contains the inputs and the outputs, with a given parameter beta, is now given by this probability distribution over I equals 0 up to n minus 1. These are all the events which we have. And then we have a P of Y, and then I'm just writing this as X in a generic way with a given beta. And this P, and this is something which we're going to shorten a little bit in the notation here. And we're just going to write this as a P of Y of I. We exclude the X's and just write this as a parameter beta. So this probability P of Y with a given beta is something which we now write out in terms of a normal distribution. So we would have 1 divided by 2 pi and sigma squared. And then we have e to the minus, and we have this y of I minus, and then we have this x of I, and let me just quickly remind you of what that parameter is. So this term is squared, and then I have 2 sigma squared. Just to quickly remind you of this notation xi times beta, this is just the specific row multiplied with all the components in the columns of the design matrix with the given vector elements. So this is an xj, xij multiplied with beta j. So this is just a kind of shorthand. Now if we now use Bayes' theorem, what we could say now, so if we take Bayes' theorem, we could now make an assumption and ask the question, what is the likelihood of having beta with a given d? Can we actually make a model for that? Now here we can now use Bayes' theorem, and we could now say that there is a probability distribution for the betas given the parameter d, and that is given, and now we are I'm skipping the normalization factor which we had previously. So I'm simply going to assume now that this is proportional, so I take away the normalization factor which was in the denominator, that this is given by P of d times beta, and then we have a model for the parameters beta. So we're assuming now that beta has its own distribution. So this is the prior, if we follow Bayes' theorem, and this is what's called the likelihood. And in our case, we have a model for that one, and that's given by a normal distribution, or a Gaussian to be more correct, because we have a mean value which is different from 0. So we could actually plug in that expression here. And now what we could say is that, okay, let us make a model for the parameters beta. So what we could say is that we model beta in the following way, P of beta, and we are now assuming that there is a product. So we are assuming that beta is independent and identically distributed, and this goes up to the number of features which we have, p minus 1, and we simply assume that beta is distributed according to a normal distribution with 0 mean value and beta j squared, and divided by some standard deviation squared, which gives us the variance. So this tau is just the variance of the parameters beta. So this is just a model which we make. Now, if we then look at the total probability, then what we are going to get is a probability for finding beta with the given outputs and inputs. So we're just reversing the question, and we're now asking what is the final probability of beta with the given inputs and outputs. That means the data which we have. So this is now simply given by this product of I equals 0 up to n minus 1. I have this normal distribution or Gaussian distribution for the y values, and that contains the exponential of minus y of I minus this x of I star times beta squared divided by 2 sigma squared and multiplied with these parameters j equals 0 of p minus 1 with the exponential of minus beta j squared divided by a variance tau squared. Now then I take the negative log of this quantity, and so I take negative log as we did in ordinary least squares, and we want to minimize this equation here, so we have the negative log of beta with a given d here, and that gives us log, and then I have a factor of n divided by 2 here, which comes from the square root. I have the negative log, so I have minus log of 2 pi sigma squared, the square root of, so that gives me plus. So I have a log of 2 pi sigma squared, and then I get plus, and now I have the norm of y minus x of beta, and this is a norm 2 divided by this constant 2 sigma squared, and plus 1 over 2 times tau squared multiplied with the norm 2 of the parameter beta. So this is in case I have a normal distribution here. And this now is pretty close to the standard cost function which we've had before. So what I'm going to do now is to redefine 1 over 2 pi 2 tau sigma. We are going to replace that with a parameter lambda. So that means that this parameter lambda, which we call a shrinkage parameter, is now going to be related to the variance in the parameter lambda, in the parameter beta. So if you look at the distribution which we had now, this p of beta, the prior, so we have a zero mean value. So this is now as a function of parameter beta. And then we have a standard deviation which gives us a confidence interval of 67% here. So this is just one standard deviation, and that's given by the parameter tau. And we know that this tau is always larger than 0. So that means that the parameter lambda, which we have defined, is also larger than 0. So if I now shrink the parameter tau squared, so that means that if I shrink here, that means I'm making my distribution more narrowly distributed around the mean value. So that means that tau goes to 0 and lambda goes to infinity. So by making tau smaller, I'm shrinking the error in p beta, but then I'm making larger values for lambda. On the contrary, if I make tau very, very large, that means that I have a very broad scatter in the value of beta, and then I have a lambda value which is becoming smaller and smaller. So you can think of this parameter lambda, which you see here, as a way to either shrink or increase the confidence interval around the parameter beta. So what this means, if we now take away these constant parameters, so we can just, if you look at this parameter here, this is nothing but a constant, and the parameters which you see here, or this function here, and this function, this gives us back the standard cost function which we had for ridge regression. C beta, and this is the C beta of ridge. When we take away the constant term, which is just y minus x times beta, and we have a constant here where we can put sigma squared equal to 1 plus lambda of beta and the norm 2 squared of the parameter beta. And this is our standard cost function for ridge regression. So it means that we have made an assumption now that the beta value themselves are distributed according to a mean value equal to 0, a normal distribution with mean value equal to 0, and a variance tau squared. And this is a kind of interpretation we can give to ridge regression. If we assume that we have such a distribution like this, multiplied with a distribution for the events y with a given beta, we can then find the final probability for beta given a given data set D. And if we do that, if we have this assumption about the parameters beta, we can then derive the standard ridge regression equations. After the break, we are going to show that lasso regression is nothing but the assumption that the betas follow what's called a Laplace distribution. So let's pause a little bit here, and if you guys have questions, please feel free to ask them. You can unmute yourself or put them in the chat. But I'm going to put the recording on pause, and then we can take a small break of some 15 minutes. Now, before we move on, I just wanted to give you an update about the in-person meeting. So the date which seemed to fit most of us is November the 7th, so that's a Monday. So that will be after the general vacation, which many of you will have. And we are going to use the whole day, but not everybody can be there all the time. So what we will do then on Monday the 7th of November is that we will have the standard lectures as we're having now from 8:15 to 10 o'clock. And then depending on your schedule, we will stay, we have reserved a room at the physics department, and we are going to use that the whole day till roughly 6 o'clock in the afternoon. And you can come and go as you want. And the idea then is actually to discuss the layout of the first project. And we can define more individual paths, but then I also have a kind of general layout for the project, which basically covers the topics we have been looking at till now, plus the additional topic of optimization problems. And next week we will also start with logistic regression and optimization problems, which we will discuss in more detail when we meet in person. Okay, so what we are going to do now, oh, by the way, before I move on, if you have some ideas, and some of you have already sent me emails about that, about topics for the data set to discuss with linear regression methods, feel free to send me ideas and suggestions. And we can always, I'm going to make a proposal for a general project number 1 to be wrapped up by, let's say, the end of the year. And then, but if you have data sets which you find more interesting than those which I'm going to propose, feel free to do so. But these are things which we can discuss when we meet in person. So I thought of just dedicating the whole day, and depending on your schedule, because I know some of you will have lectures and some have not lectures at different times of the day, you can just come and go as you want. Okay, so the discussions which we had before the break was actually now to use Bayes' theorem and assume that the parameters beta follow a normal distribution with 0 mean value and a variance tau squared. And when we do that, we can then develop a posterior probability and we have skipped these normalization factors, which just give us a constant, then we have a probability which simply runs like a normal distribution for the outputs y of I, multiplied with a normal distribution for the parameters beta. And that gives us the probability of beta with a given variable or input and output variables d. And when we took away the constants which you get from this 1 over 2 pi sigma squared, we just leave that out because that's just a constant and it's not of any relevance when we're taking the derivatives in order to optimize the cost function. We ended up with a function which looks like this. And then we simply change the lambdas to, taus to lambdas, and then we are back to the equation which we had before. Now if we do the same thing with ridge regression, the assumption then is that lasso, in the lasso case, we have a parameter beta which follows a Laplace distribution. And this, if you click on the link here, you will get a direct link to the description of a Laplace distribution, which is a distribution which is looks more like a wedge and peaked around the mean value 0. And this is just given by an exponential with the absolute values of beta. In that particular case, when we repeat the same exercise by taking the log of this product and skipping the constant parameters which come from 2 pi sigma squared, we end up with the same equation which we had for lasso regression. So we can actually interpret lasso and ridge in terms of a probabilistic point of view, where we assume that the betas have a prior which are distributed according to either a Gaussian distribution or a Laplace distribution. And this has also consequences when we now are looking at the results. And in order to do that, what we can do then is to look back at the Jupyter notebooks. And let's now look at some of the examples which you have. So these are the examples which we went through last week. But let's now, after we've done this link with a statistical interpretation, let's now look at some of the examples which we have here and the discussion of a specific result. So what I have here is a function which is given by e to the minus x squared plus another terms which runs like x squared plus some random noise. And what I'm doing here now is to perform first a standard ordinary least squares, and then I'm performing both a ridge and lasso regression. And in this cases here, I'm actually including the intercept by having an intercept equal false for both ridge and lasso regression. Now, this is again a case where ordinary least squares does a better job than lasso and ridge. So I'm setting up a set of parameters lambdas, and I'm only looking at 4, and they are set up in terms of a log scale. So I have 10 to the minus 3 from 10 to the minus 3 to 10 to the first. And then I look at the values of my polynomial fit. And if we now just run this calculation here and look at the results which we have, if you now look at the mean squared error which I get for this specific function with ordinary least squares, this is actually not a very impressive result, by the way. So it's a 1.01, so it's not a very good mean squared error. Now, when I now have a parameter of lambda, which is 10 to the minus 3, which is the one you see here. So the first one here is for ridge regression. And you see now that with the lasso regression, we have already, at this value of lambda, we have already squeezed down some of the parameters. I mean, the parameters, we are fitting a function given by x squared, and by the way, this should be, I think this should be plus 1 here. Let me just bring that one up here. I think there was a small error here. Let's rerun it, because we had some parameters which accidentally became 0. So the this is a fourth order polynomial we're fitting, so this is the intercept term. This is just the first term, the second, the x squared, x cubed, and x to the power of 4. So we are fitting a fourth order polynomial. And in this case here, you'll see that Lasso and Ridge, after some calculation with values of different lambdas, we see now that they tend to squeeze down the values of the other parameters. And at the end, you see now that with the Lasso, I get actually a result here where the mean squared error just keeps growing because I'm actually running all the parameters down to 0. So the only thing I have left then is the input value y. And the thing which is interesting to look at is if we now use Bayes' theorem when we run these calculations, we can now think of this in terms of the changes of the parameters beta in front of the polynomial fitting which we are doing as parameters where we now try to with a given lambda we are trying to traverse the data and get the best optimal mean squared error. So the problem with Ridge and Lasso regression is that they tend to run down the parameters and make them smaller and smaller, as we can see here. So Lasso drives the parameter to 0, as we discussed last week, whereas Ridge regression makes them smaller and smaller gradually, and you can see that in the fits here. And clearly, when you increase the value of lambda, you're getting an error which becomes larger and larger, and you get a mean squared error which is actually not very good. So if we now perform this kind of interpretation, if we go down here and look at the example again, so let's now rerun this example. If we rerun that code, what we are going to do now is to rewrite the coefficients beta y as function of the polynomial degree and noise. So in this case, we are going to focus only on the Ridge results and some few selected values of the hyperparameter lambda. So if we don't include any noise and run this code for different values of the polynomial degree, what we will see then is that the results for the beta y do not show great changes from one order to the next. That is an indication that for higher polynomial orders, our parameters become less important. So we are getting a better and better fit, but most of the weight is carried by the low order degrees of the polynomial. If you add noise, on the other hand, what happens then is that the function values we want to reproduce are going to fluctuate much more. And what happens then is that the polynomial fit is trying to adjust the fit in order to go through and represent all the data points and give the best possible representation of the data points. And that can lead to large fluctuations in the parameters beta I. And this is also reflected in a larger value of the variance for each parameter beta y. And what Ridge regression and also Lasso as well are doing is then to try to quench these fluctuations in the parameters of beta y, which have a large variance. So let me try to show this by looking at a figure, and then we're going to run the code afterwards. So let me see if I can explain this in simple ways, what is going to happen. Because this is related to the problem of overfitting and underfitting, which is coming pretty soon. So if we now look at, suppose we run a calculation here, and we are looking at a polynomial of a certain degree. So we have on the x-axis here, we have what we call model complexity. And this could be a polynomial to a certain degree. So let us assume, like in this case, we have a polynomial, we are fitting a function, f of x, to a polynomial of degree 4. So we would have a beta 0 plus a beta 1 times x of I plus a beta 2 with x of I squared plus a beta 3 with x of I cubed plus beta 4 of an x of I to the power of 4. So this is what we want to fit. And then when we now look at the data sets, what we could get then, we could have a function which is nicely fitted. But if we look at the parameters beta now, so we have a model complexity here, and the data could be something, so let's now look at this f of x. So we could now have a function which varies widely, something like this. So these are the data points which we want to reproduce. Now, depending on the smoothness of the data, we can get a model which traverses the data easily, or we can get a model which from order by order in the polynomial fit struggles more and more in reproducing the data. When you have this specific case, what happens then is that the parameters beta may vary a lot. But let's look at this specific function here. And suppose we made this fit model complexity of degree 4, and we look at the parameters beta. So we would have a beta 0, a beta 1, a beta 2, a beta 3, and a beta 4. So what could happen is that this has a value here, and it could have a variance like this. It could have a value here with another variance, a new value. So these are just schematic results like this. So this is what I indicate here is actually the deviation from the mean value. So this could be one model. So this would be model 1. And this could be a model with noise. Now what I could also do now is to run a new model where I get where I don't have noise. So we could have a model 2 with no noise. And what you will typically see then, so we could have a mean value here for beta 0, but then often what happens is that the parameter beta has a much smaller standard deviation because the noise plays less role and it's easier to fit the data points. So we would then often see a situation where we have a small variation around the parameters lambda. Now if I now increase the model complexity, so suppose we go from a model with no noise or model with noise, and then we increase the complexity, and we then go from a model which had a polynomial degree 4 to a polynomial degree 5. So we do a beta 0, we have a beta 1, a beta 2 here, a beta 3, and a beta 4, and then we have a beta 5 here. So in a model with no noise, what could happen then is that the parameters we get, the parameters beta 0, show little difference. So if this one has now a value of 3, this would also be close to 3. And then I have this parameter here, and suppose this has a value of 2 here, and here again this has a value of 2. What we would see then is something which does not differ so much from the previous case. And we would have a small variance in the parameters beta. On the other hand, when I now look at the other model, what could happen then is that I could get something which goes like this, when I now fit a different model. So I could get even larger variations. So this is very schematic. Now the reason for these larger variations, so I could get this one up here, something like this, and I could even get something which varies widely here. So what is happening then is that if I look at my blue model, I'm now trying to go through all the data points in case of noise. So this is a noisy model. And when I increase the complexity of the model, I'm now tweaking the parameters to better and better reproduce this data. So that means that my data, I will try it with an increasing model. I'm now trying to make something which goes through all the data points when I increase the complexity. When I increase the complexity, what happens then is that I'm trying one to go through all the data points, but this will also lead to parameters beta, which will change from model complexity to model complexity. So let's take a look at the code and see that this is indeed the case, that these parameters can, if we do a pretty good fit, vary little from order to order in the model complexity, or vary a lot if we have noise. Now, if we make a model very complex and try to traverse all the data, this can lead to overfitting, in the sense that we fit perfectly the training data, but when we apply this to data which was not included in the training, we may fail miserably when it comes to the value of the mean squared error in our case. So let's go back to the code and try to see if we can see what's going on here. And we are going to limit ourselves to ridge regression. So let me just quickly change this one. It should be a +1 here. And in this particular case, I take only 5 lambda values. And just a small moment, because I think, no, this is the code we are going to look at. So we are just going to look at small lambda values. We are going to do ridge regression only. And we split the data into test and train. And then we are going now to drive these parameters slowly and slowly to smaller and smaller values when we increase the value of lambda. And let's now just take a quick look here. So you see now, we start with a polynomial of degree 4. And we have a noisy model. So we have included the noise in here. Now what you see now is that the values of the parameters for the different values of beta, they change obviously when we now include high and larger values of this parameter lambda. So we are reducing the mean, now we're actually increasing the mean squared error. But you see the way the parameters lambda change here. Now, if I now increase the complexity of the model, so let's just keep 2 values of lambda here and just run them, because then we can keep the parameters in mind. So you see now I have a parameter beta 0, which is 0.9. Now if I now change, so what you also see is that lambda is now squeezing the value of the parameters beta. It's actually going to give a smaller variance for these different parameters, so it's actually squeezing away some of these parameters which vary a lot. Let's now increase the order of the polynomial to 6. And let's see what happens when we have all this noise here. And just let us now look at the values for lambda equal 10 to the minus 3. So you see now a parameter here which is 3.9. We have a parameter 0.9 minus 0.02. So if we now rerun it, you see now that these parameters, the beta 0 doesn't change much, but all the other parameters have changed considerably. Now what ridge is doing, and lasso as well, is it's actually shrinking some of these parameters. So you see that all the parameters have been made smaller except the one for beta 0. In this specific case, what it does is that it gives us a mean squared error, which is poorer, because it's driving the higher order coefficients to smaller and smaller values. But what you see now, if you just look at these results, is a big change from order 5 to order 6. So in order 5, this was minus 0.2, and now it changes to 1.4. And that's because we are trying to adjust the parameters to go through the data in a better and better way. So if I now take away the noise and I repeat these calculations, then I'm going to get a function which is smoother and easier to fit in terms of a polynomial. So in this specific case, we took away the random noise, and let's now rerun this for a smaller degree of the polynomial. So keep in mind just this number here, 0.1 and minus 0.83. So if you rerun it with a polynomial degree 5, you will then see that the difference between these parameters are not that large when we move from one polynomial order to the other one. So it was 0.1 and now it's just 0.11. This parameter was also pretty close. So what you see now is that when we reduce the order of the polynomial, the parameters are actually not varying that much. Now with ridge and lasso regression, what you're doing then by tuning this parameter lambda is that you're actually reducing the spread in these parameters and you're driving them slowly and slowly to 0. And the thing which is interesting then is actually the behavior of the polynomial fit and the parameters beta as you keep increasing the polynomial degree. And if your data are very messy, then these parameters will change a lot from model complexity to model complexity. If you have a smooth function, these parameters will not change that much when you add a complexity to your model. They will actually become smaller and smaller as you increase the complexity of the model. And you can see that if you look at the fourth order parameter, 0.06, if we now change back to a sixth order polynomial here, what we are going to get is a parameter here which doesn't change dramatically much. And also the high order parameters tend to be smaller and smaller. So this is a kind of flag which tells us that probably we may be, when we have lots of noise, we may actually be overfitting the model to traverse the data, and then probably we will have a prediction on test data, the unseen data, which actually is not that good. And this leads us to the next topic, which deals with resampling techniques. So we are going to move into this topic here because there are two central techniques which are used in resampling the data. And why do we resample? So we need to rethink a little bit what we've been doing. So we have overseen some quite important features in the data which we have, and also in the way we treat the data. So let me bring back the notebook and set up a kind of general image which you're going to meet when you run calculations. And this leads us to some central topics. So let's now put up resampling, which then is also linked with the problem of underfitting and overfitting of data. So let's make a general observation first. Suppose we are calculating the mean squared error, and then we have a given model complexity on the axis here. So in our case, this could be the degree of a polynomial, and we are plotting the mean squared error. And suppose now we have a low degree, so this could be a polynomial of degree 1. We could have a polynomial of degree 2, 3, etc., all the way up here. Now if I plot the mean squared error for the training data, let me ask you now, and you can decide whether you want to respond in the chat or whether you want to respond by just unmuting yourself. So if I plot the mean squared error of, let's say, a polynomial fit as a function of model complexity, what I would see now is typically something like this. And let's say to third order, I'm getting a better and better training. So this is my training data. So this is how I construct my model. So what is your expectation of the behavior of this curve when you increase model complexity? Will it increase or will it just keep decreasing? What do you expect from you fitting a model with a given complexity to the training data? So any good suggestions? You can use the chat or you can just unmute yourself. So this curve, is it going to decrease or increase? Any good suggestions? So if you have a given set of training data, what is your feeling about the behavior of the mean squared error as a function of the model complexity when you now use only the training data? So is this curve going to keep decreasing forever or will it just increase at some stage? So I'm just looking after general trends. Now feel free to answer in the chat. So you could just write increase or decrease. Doesn't seem that anyone wants to answer in the morning now. So I can give you the answer here. So this curve is actually going to decrease continuously. So when you increase the model complexity, you can actually drive this to a perfect fit with the data. And this is what we saw in the previous cases, that we can actually fit better and better model, in particular if we don't have lots of noise. So it means that when we look at the training data, we are going to have a curve which decreases continuously. So we make a better and better fit. It depends a little bit, however, on how much data you have. So you could get cases where it could increase, but that is often linked with you having too little data to train a model, and also it could have to do with accumulation of numerical errors. But in principle, if you have lots of data, the more you increase the complexity of the model, the better the fit. However, if you now plot the mean squared error for the test data, so now we take the red here, so we have test here. So this is our mean squared error for test. So we are making a better and better fit. And now we have a model which has been trained on a specific data set, and then we simply apply this model to data which has not been included in the training. So this is normally called the test data. So this is unseen data. It could be us just generating new data. So what is your feeling about this curve? Will that just keep decreasing, or is something else happening? So feel free to use your intuition here. So let me see now. There's an answer in the chat here. It will increase at some point. Excellent. So what we are going to see then is something like this. So this point where it starts, where it finds its minimum here, on the test data which we are looking at, this is a sign of where overfitting starts. What it means is that we have now done such a job with fitting the training data that our model, when it suddenly gets data which it hasn't seen, it doesn't know how to treat that data. And you could see an example where you now have a curve with your data points, which look like this. So this will be your model data, the red color. So we can have x and f of x. And we have now fitted a model which actually goes through all the data points, like this. However, if somebody now gives you a new data point, which is up here, or down here, if you use this model, which has been so finely tuned to the training data, you would fail miserably. So the whole thing now, and which everything rotates around, is the fact that many of these methods which we are dealing with are data greedy. The more data, the better we can make the fits. Now, however, that means that in most cases we do not have access to so much data. If you run a nuclear physics experiment, a typical run would be from, let's say, 2 days to a week or perhaps more. And such an experiment has a price tag of millions of euros. And if you fail, or if you don't generate enough data of high quality, it's not very likely that you will get more beam time in order to generate more data. So the data which you have, you can state that very simply, is the data you have. In many calculations in theoretical nuclear physics, like if you're doing a lattice QCD calculation, lattice quantum chromodynamics, you can run for months in order to just produce some, let's say, 1,000 data points or expectation values. And that is normally something which can be on the border side when it comes to get good enough statistics. And that is where resampling techniques kick in. So resampling techniques are ways to, in a way, produce new data sets without actually rerunning an experiment or rerunning a heavy calculation. Now, many of the examples which we have been looking at here till now, these are so-called vanilla examples, in the sense that we can easily regenerate more and more data. So for the examples which I've showed you, we could now just define a huge data set, and then when we fitted the model, we could just generate a new data set easily, and we could use that as a test data. So that means that the kind of models which we have looked at till now, they are pretty easy to use and pretty easy to generate larger and larger data sets. But in real life, we are normally faced with the data which we have. If you, for instance, conduct a survey over, let's say, a specific illness like heart disease, and you survey thousands and thousands of people over, let's say, 3 or 4 decades, the data you have are the data you have. And it's very unlikely that you will make another survey which lasts another 3 to 4 decades. Which means that we need to think of ways by which we can, one, estimate a reliable error, a reliable mean squared error, a reliable mean value, a reliable variance with the data which we have. So if we now look at these resampling techniques, there are 2 basic techniques which are widely used in machine learning. So one is called the bootstrap, and the other technique is called the cross-validation. There are other ways of using these, of regenerating or resample data. Cross-validation. The aim with these methods to provide reliable statistical estimates of quantities like the mean error, the mean value, quantities like the variance of a given variable. Like if we are looking at the parameters beta, we want to estimate the variance of these parameters in a reliable way, like mean values, and variances and variance and the variance, and mean squared errors if we are doing a regression problem. So these are just examples of statistical quantities. So let me remind you, for instance, the mean value, what that one actually looks like. So the mean value, mu, of a given variable is given by the sum over the number of observations we have, I equals 0, of n minus 1, and then we have some observation x of I. The variance, if we look at the unbiased variance, sigma squared, so this is the unbiased, and that's why I have this factor 1 over n. This also is a sum which runs over n minus up from I equals 0 up to n minus 1. So this would be x of I minus mu squared. And these are sample expectation values. And they are not so today is my day when I don't write properly anymore. Expectation values. So these quantities, they may not be equal to the exact quantities if we knew the probability distribution. So that means that they are estimates of the true mean values or the true variance or the true mean squared error. So like the mean squared error, which we have defined like 1 over n, and then we have the sum of y of I minus this x of I star times beta squared. This is also written as the expectation value of this quantity y. If we now write it in a vector form and matrix times a vector form, this is given by this quantity here, the expectation value. Since we are summing over 1 over n, we divide by 1 over n and sum over all the data entries. So this could also be thought of as a sample mean value. Now, if somebody were to give us the correct distribution, we should be able to calculate the exact mean squared value with that specific model. However, since we don't know this distribution, we are then limited to make a sample expectation value. So the question now is, can we, with the limited data we have, can we give a good estimation or good estimate? Can we give a good estimate and reliable of various sample expectation values? And this is where actually many of these resampling techniques come into play. Now, the bootstrap technique is extremely popular. It's very easy to implement, and it has mainly been applied to independent and identically distributed data. And it's a way by stochastically resampling your whole data set again and again and again. It should then be able to, and you can prove it, that it should then be able to give you something which approaches the correct mean value and the correct variance, and that means also the correct mean squared value. So that is one method. Another method which we are going to use quite a lot, which is used actually quite a lot in machine learning applications, is the so-called cross-validation method. So these are two central techniques which we are going to spend some time on, and we are going to use these techniques to get an estimate of the mean squared error in regression problems, of the mean values, of the different parameters, also of the outputs, and the variance of the parameters. So that when we have run these resampling methods, we can then state that the mean squared error, which you see here, and which we now have evaluated by resampling techniques, is the best we can provide. Similarly, with the various mean values and other expectation values like the variance, the aim of these techniques is to provide, within the data set we have, a reliable estimate of these quantities. And for some of these methods, you can actually prove mathematically, and this is the bootstrap method, that the bootstrap method converges actually to the correct variance after a given number of bootstraps. So let's now try to look at these methods, but I see that my time is over for today, and we are going to start the next lecture by looking at these resampling techniques, because they form they are actually central ingredients in all machine learning methods. And the whole philosophy is that they are going to aid us in getting better estimations of quantities like the mean squared error, or the variance, or the mean value of a given variable which we are looking at. And this is important because then we can state with some kind of certainty that these are the values which we expect from the specific model we have developed. And we can then with some certainty say that these are the expectation values or the mean squared errors of our specific model. And this is the topic for next week, and we are going to look at various statistical properties and also introduce these resampling techniques and see how we can implement them and use them in connection with the various machine learning algorithms we're going to study. Okay, I'm going to stop my recording